Hi everybody, my name is Conor O'Riordan and I work in the dark matter group at MPA in Garching. So I'm going to talk today about dark matter, maybe at the smallest scale discussed so far, and that's at the subgalactic scale, where I use strong lensing to investigate the properties of dark matter at that scale. So what is the kind of thing that we look for? In all particle dark matter theories, we expect there to be this very large population of low mass halos. So for me, low mass is between 10 to the 6 solar masses and 10 to the 10. And this is kind of the range that we're sensitive to with our method. And this is interesting because in cold dark matter, there should be many, many of these small halos inside, all galaxy scale halos, hundreds or thousands of them. And if you look at these zoom-in simulations here from Mark Lovell, in warm dark matter scenarios, that's where the particle mass is smaller, these very low mass halos don't form. And the ones that do form are much less concentrated. So the dark matter model is affecting both the number, the mass of these low mass halos, but also their intrinsic properties, their profile, concentration, etc. I'll talk a little bit also about self-interacting dark matter. And the signal we're looking for in that case is this core collapse process that happens in self-interacting dark matter subhalos, where you end up with subhalos which are much, much more concentrated than you would get in CDM. So what does this actually look like? Well, it doesn't look like this in practice, but this is a highly exaggerated version of the kind of signal that we look for in a strong lens. As a low mass halo, when a low mass halo is near to the arc, you get this very characteristic sort of break in the arc, or a little kink or a pinch or some kind of shape that you can't reproduce with the sort of global mass profile of the lensing galaxy. And it's exactly this kind of signal that we look for in strong lenses. So to do this, we need very precise modeling, and we use a modeling code called Pronto, which was developed by Simone Vegetti and extended by others, including myself. And the way this works is that once we've modeled the lensing galaxy, any other mass in the line of sight that might be doing some lensing, and the background source, we then look for these small corrections to the lensing potential. So we have a pixelated grid that represents the potential in the plane of the lens, and we make small corrections which gradually improve the fit, improve the residuals with the image, and what we're looking for when we convert this to a density map are concentrated over densities on this pixelated grid, and that reveals a low mass halo, which then we can characterize with parametric fitting. So that's how we detect subhalos. But to actually say something about the properties of dark matter using detections or non-detections, which is more often the case, we need something called a sensitivity map. And I show here a sensitivity map from one of Julia Spali's papers. And this is basically a map of the lowest detectable subhalo mass that you could detect anywhere in your strong lens image. So once you've made your detections and non-detections, you have a dark matter model that makes predictions about the number of subhalos of certain masses in a certain mass range. And if you didn't detect them, the sensitivity map allows you then to come up with a likelihood for that dark matter model, given that you now know what you didn't detect, if that makes sense. So this is a very important ingredient. The sensitivity map, unfortunately, is very difficult to calculate in a classical way. So I'll explain a bit about some work I've done on that. First, I want to talk about NGC 6505. You may have already seen this image. I'll take any excuse to put this into a talk. But this is some of the most recent work we use Pronto for. This is the first strong lens found in Euclid, very rare, low redshift strong lens, and a very beautiful image. So ESA were very keen to publicize this, and it made a lot of publicity all over the world, also in Hungary. And it's not just very pretty, it's also very useful for our science. So here's some modeling from Pronto on the left. And I show here the source reconstruction is very compact, very bright object. It's very, very bright for a strongly lensed source. This gives a huge signal to noise ratio and makes this very useful for looking for these core collapse SIDM subhalos, because this object is essentially at redshift 0. And so you've got kind of the maximum cosmic time for this core collapse to have happened. And using Punto, there's a sensitivity map here for just the brightest part of the arc. And we're able to find masses down to about 10 to the 8 solar masses in the very brightest part. So this is ongoing work that this is what this is useful for. So this sensitivity map that I show here, you'll notice it's only a very small part of the arc. To compute this alone took about a week of CPU time. If you're interested in why it takes so long, I can explain later. But a lot of the work that I've done in the last few years is to come up with a better way to calculate this using machine learning. And that's necessary because we've got loads of lenses coming from Euclid. We already have loads of strong lenses that we haven't sensitivity mapped because it's simply too difficult. And so this method is a step to try and correct that. It very simply detects subhalos in a strong lens image. So it just tells you is there a subhalo in here or not. It's trained on a huge variety of lens and source configurations, data qualities, and then to produce a sensitivity map, we take the lens that we're interested in mapping, and we've produced simulated versions of this observation with a test subhalo moving around the image, looping over many masses, and pass each of those through the trained subhalo detector. And then you simply record the probability with which it was detected or not. And choosing a detection significance then gives you a sensitivity map, just like this one here produced classically. Now the training time for this neural network is very long. It takes weeks to train. But once you've trained it for a specific instrument, so it learns the sort of data quality of that instrument, it can be used now to produce sensitivity maps in a few seconds. Basically, the constraint then is just ray tracing simulated images, which can be done very quickly on GPUs. So we can produce something like that in minutes instead of weeks. Now, there's been published a couple of papers with this method. We've had a few nice results from it. I'm going to talk today about the third paper, which will be on AstroPH on Thursday. So look out for that. This is very recent stuff. And this paper deals with something that's come up in a couple of papers. It's never been systematically looked at. It's a very interesting phenomenon, which is basically to do with that when we do this sensitivity mapping, this potential corrections type of stuff, we're always considering, a single large perturber. So something large enough that alone it changes the lensed images enough that you could detect it. But of course, in CDM, there should be hundreds of thousands of low mass halos in and around these strongly lensed arcs. So the question is, even though none of these could be detected alone, can they be detected because they're huge numbers? And this mass range in which this sort of population of undetectable objects lives is the most interesting. So this sort of 10 to the 6, 10 to the 8, 10 to the 9 solar masses. These are the subhalos that wouldn't be there in warmer dark matter models. And these are the subhalos, depending on your SIDM model, that could be most likely to core collapse. So what we do is we take the trained substructure detector. We use this to make sensitivity maps for 100 HST-like strong lenses. This gives you the minimum mass that you could detect in each of those images. From the dark matter model, we get the subhalo mass function. And the combination of these two tells you, for that lens, in an average realization of CDM, how often would you make a subhalo detection, given that subhalo detections are always an individual object. Then, using that population, that CDM population of objects, we create realizations of those same systems that we just sensitivity mapped, but now we inject the entire CDM population of subhalos, all the way down to 10 to the 6 solar masses, and we run those same objects, the same images, through the substructure detector. So if the only signal in the data is these big halos close to the lens images to produce a detectable effect, if the only signal is from those, then these two things should agree. So the sensitivity map should correctly predict the number of detections that the substructure detector actually makes. Now you can probably see what's coming, because otherwise I wouldn't have written a paper about it. But I'll start with the prediction. So you want to read this plot kind of right to left. So on the x-axis is what I call the cutoff mass. basically what I do is when I draw this population of subhalos, I discard all the subhalos below a certain mass. The idea here is to get an actual mass limit on what this population is. So starting at 10 to the 10 solar masses, these are all huge, individually detectable objects, but there are very, very few of them, right? So we get very few detections. This is the rate of detections here on the y-axis. As we start to add more objects, the number of detections goes up, and eventually it flatlines because we've kind of reached the end of the sensitivity of the data. Once we get sort of the high 10 to the 8, there's no more sensitivity left. So everything you add is not detected. And sort of limiting case, we get 5 detections per 100 HST lenses, which is actually what we do get in reality, roughly, with real HST data. So now that's the prediction from the sensitivity map. And this is what we get from the substructure detector. So starting again at 10 to the 10 solar masses, in this regime, they agree because you have very few objects and they're all detectable. So there's nothing strange going on in the data. As we go down to 10 to the 9 and lower, now there seems to be more detections made by the substructure detector than the sensitivity map predicted. But all of these objects up here that are now being detected individually would be undetectable. As we go very, very low masses, this increase sort of stops increasing because at some point, even though you're adding a huge number of objects, they're individually so small they can't even be detected together. So I'll conclude there. And the point here is basically that we're throwing away most of the information in these strong lens observations when we do this kind of dark matter inference, because we're only thinking about big, individually detectable objects. And probably we constrain something like the half mode mass of the dark matter particle down to another order of magnitude or more than we're currently able to do with strong lensing. And it's the low mass halos in this exact mass range which are the most interesting in terms of the dark matter model. So in Euclid and eventually Roman and SKA, when we have many, many tens of thousands of strong lenses, incorporating this population effect correctly will make all of this data a much, much more powerful dark matter probe. So I'll finish that. Thanks.
For one question. It's very technical. I don't know if someone wants to ask a physics question. I'm curious about why it took weeks or
Which part, sorry?
The part where you said to get the image took like a week.
Right. So to produce something like this, what we do is we model the strong lens, which is essentially what's on the left. Then we take that model, we add noise as in the real observation, and we add a perturber, moving through every pixel and every mass range. And for every single one of those, we compute Bayesian evidence for that model versus the smooth model, so the model that has nothing. So this involves a lot of computation time, basically. Yeah, and each one involves a full sort of strong lens model, multi-nest evidence. So yeah, each one of those, I mean, this is a Euclid lens. So in our code, this could be modeled in a few minutes. But when you multiply that by so many iterations, it becomes a problem.